So we're going to take some time today and we're going to talk a little bit more about chemical reactions. And so we have one here, which should look pretty familiar to you. We have some hydrogen reacting with oxygen, and we've got our arrow to produce some water and some heat. Okay, so we already know that this is a synthesis reaction, right? We've got two items coming together to form a last one. So we could tell right now that this is a synthesis, okay? And we can also tell that it is exothermic because the heat is on the product side. But I'm here to tell you we kind of left some things out. So not every reaction just goes from reactants to products. Sometimes, and this is the tricky part, sometimes actually it can go in reverse. When it does that, it forms what we call a dynamic equilibrium. So there's a new phrase for us. So let's talk a little bit about what we mean by a dynamic equilibrium. So let's start thinking about this idea of a dynamic equilibrium, and we're going to think about it in terms of a manufacturing plant. So here's a model of a factory, and we have this factory which is restricted to 100 employees. So they have 100 employees in the building at any one time, and throughout the day 20 employees will go on break every hour. And when they do, that means 20 other employees are returning from break. Okay? So this factory is in a dynamic equilibrium because just as many employees are coming in as are going out, but the total number of employees in the building is going to remain constant at 100. Now these employees go in and out for their break by going through a checkpoint. So they have to punch in and then they have to punch out. So I think about, what do you think would happen in our model if that check-in and check-out system was faster? What would happen to the number of people in the factory? We can also use the same thought process when we're looking at chemical equilibrium. And in this reaction that we have here, the reactants here, these are the employees that are inside or going out of the building, and then these are the employees that are coming back into the building. And our double arrow here, that's our checkpoint. Okay, so that's where they're checking in and out. All right, so if they're heading off to break, it's the forward reaction. If they are coming back from break, it's the reverse reaction. So heading to break is forward reaction, and let me get rid of this, and heading back from break is the reverse reaction. So think about the factory example when you answer the next question. So when you have a reaction that is at equilibrium, that will mean always that the rate, or how fast the forward reaction goes, so however fast the forward reaction goes, that's going to be equal to how fast the reverse reaction goes. Okay, so just like when we were talking about kinetics, the rate of the forward reaction is going to be equal to the rate of the reverse reaction if a reaction is in dynamic equilibrium. Now, if a reaction is at equilibrium, you can actually change that equilibrium. You can stress the system by changing something. And I have here a model up top which tells you what happens when different stresses occur. But what I want to do is I want to talk about how to visualize this. So I'll leave these guys up here, so you might want to pause the video and write those down in your notebook. Those are helpful to have. But let's think about a reaction in terms of a seesaw or a teeter-totter. Depends on what you called it when you were a kid. So right here I have a representation of a seesaw or a teeter-totter, all right? And on the left side of the teeter-totter, I have reactants. And on the right side, I have products. The double arrow is right here in the middle at the fulcrum, all right? So this represents a reaction at equilibrium, meaning that the teeter-totter is perfectly balanced left and right, okay? So as we apply some of these stressors to the reaction, let's say going back to our reaction that we've been talking about. So if we have our at equilibrium, we've got our 2H2 and our O2. Those are on the reactant side. All right, there's our arrows, and we're forming 2H2O and our heat. Okay, and when it's perfectly at equilibrium, it's going to be nice and flat. So think about, what if we increased the amount of H2? What would happen to that teeter-totter, that seesaw? So if I added more H2, meaning I'm adding some right here, what would happen to that seesaw is initially that side would go down, right? So the side that has the H2, if I'm adding more, it's more weight, right? It would come down. So if we want to make this teeter-totter go back to being level, but we can't take anything off, what would have to happen? Well, if we want to make that go flat, everybody on the teeter-totter is going to have to shift to the right. Because if we shift it to the right, then the weight on this side, of the teeter-totter is going to get a little bit bigger, and the weight over here is going to get a little bit smaller. And so the teeter-totter, once that shifts, will come back to equilibrium, be nice and flat, all right, because everything has shifted away from where I added and become flat. So think about, what if, so let's do another one. What if instead of adding H2, what if I decreased or took away some O2? What would happen to the teeter-totter? Well, initially, since I'd be taking away from the reactant side, initially that teeter-totter would do that. So now, and think about, what would happen to the equilibrium what would happen to make this go back to equilibrium? Which way would it have to shift? And now think about, what if we increased the temperature? If we increase the temperature, right, that would be like adding heat, okay? We're going to be adding heat. So if we added heat, what would happen to our teeter-totter? Well, initially, it would look like that. So which way would that have to shift to bring it back to equilibrium? And then the last question, I'm going to give myself some more room because I used up all my room. The last question, so what if we then decrease how much water we have? What would happen there? Well, we're taking it away from the product side. So our teeter-totter would initially look like that. So which direction would the equilibrium have to shift to go back to flat in this case? So now on the next section, you're given a chart, and I am asking you to predict which way each of those reactions would shift.